Hola amigos, so now let's move on to our next topic, that is takeoff performance. At page number 458 of the book, we are following Introduction to Flight, chapter number 6, element of airplane performance. And here we have this aircraft which is taking off by moving a distance sg, that is the ground distance, okay, and s ground sg is denoted for this ground distance, and this aircraft will travel this ground distance from zero velocity till takeoff velocity. It will keep on accelerating, okay, and it will its acceleration will keep on increasing as it reaches up to a velocity of takeoff velocity at the end of this st, and it will move on with takeoff velocity for this flaring distance, which is known as s rotation, sr over here. For 3 seconds it will flare like this, okay, it will flare like this. It was moving in the ground like this, and then it will flare for, it will like flare like this for 3 seconds, and then it will move in a transition phase to move towards a climb, okay. So here we have this s transition and this is s climb, okay. These are measured on the horizontal distance, okay. So this sd is over here, and these all we will cover in the next topic, or next lecture, sorry. So here we have the aircraft who is preparing to take off from this zero velocity to takeoff velocity, and here we can see the aircraft is experiencing thrust force to keep it moving in the forward direction, and drag force opposite to the direction of velocity, okay, and lift force perpendicular to direction of velocity, and weight downwards. And these forces are then resolved or in the direction of velocity, so that we can compute at what acceleration it will be taking off or it will be moving, okay. So here we also will be seeing that during the flight the aircraft will have only the lift, drag, thrust and weight, but here on the ground it will experience the friction because of the ground, and that is, friction is always the friction coefficient of this earth, and then this friction coefficient when multiplied with the normal force will give us the force that should be applied to move forward, so that it could overcome the frictional force of the earth. Like we want to move with some velocity, and that velocity can only be attained if we overcome the amount of friction that is applied by the earth, okay. So the frictional force is given by r over here, which is acting opposite in this direction, opposite to the direction of movement of aircraft, okay. Aircraft in this direction moving, and frictional force is in this direction, and which is equal to r, and that's mu times w minus l, because when the aircraft is on the ground the weight is higher than the lift. Once it attains lift equal to weight, it will have some lift to move upward, it will have some force to move upward, okay. So at least it should be having lift equal to weight, so that it's the aircraft wheels should should move up with the aircraft, okay. So here we can see the thrust force and takeoff performance, or say takeoff equation for this ground distance performance is given by equation of motion, which is this, that is equation of motion for the ground distance is given by T minus D minus thrust minus drag minus frictional force minus mu times W minus L. So this W, if we see, we know from our earlier lecture that weight of the aircraft will keep on decreasing because the amount of fuel is getting consumed with time, and as the aircraft keep on moving, the weight of the fuel gets decreasing, and hence the weight of the aircraft will also decrease. So this weight we are observing over here is actually the takeoff weight, okay. So till SG we assume that takeoff weight till this total I'm talking about takeoff portion, which is from starting 0 to S climb. From 0 to S climb we assume the weight of the aircraft is W takeoff, which is constant, we assume for preliminary design, and which we have done over here as well, that is thrust minus drag minus mu times W takeoff minus lift, okay, because weight is acting downwards and lift upwards. And from here we know mass of aircraft is actually W takeoff by G, and the acceleration we are talking here, as I said, it will keep on accelerating, and it will its acceleration will keep on increasing. But the equation of motion we know from elementary classes is there are 3 types of equations for equation of motion, and those equations are valid for constant acceleration. So here we are doing the same thing which we did in our elementary classes, that we assume the average acceleration over this period, okay. So from 0 to SG we are observing over here, okay. So for this SG distance we are saying that acceleration which is increasing, we are taking the average of that acceleration, and that average of acceleration is then observed for the takeoff velocity which is achieved over here, and that velocity which is takeoff velocity that is achieved over here is taken for 70% of that velocity, okay. For 70% of that takeoff velocity, the average acceleration is taken for this aircraft for moving from 0 to this SG distance, okay. So what do we mean by the 70% of this takeoff velocity? That is the aircraft when it will be taking off, it will have a velocity which is v takeoff, okay, which is actually over here, that is v takeoff is actually the 1.2 times of stall velocity, okay. So basically it's increased, it has increased by 20% of the stall velocity, okay. The takeoff velocity is 20% increase in the stall velocity, and we have taken the 70% of this takeoff velocity, okay. And that 70%, at that 70% of this takeoff velocity, we are taking the average of this acceleration, and then we are applying the equation of motion, okay. So coming on to this 70% of this takeoff velocity, we have the drag and lift over here, which varies with the velocity, and here takeoff velocity, and they varies with v square, because from this formula you can say, you will get to know from here and here as well, if lift is equal to weight, then lift is directly proportional to v square, and drag also is directly proportional to v square. And for other practical purposes, we know the drag the thrust also varies with the velocity. So we can say over here the thrust also is at 0.7 times of v takeoff velocity. Okay, so we can neglect, but for the time being we know that thrust is also 0.7 times of v takeoff velocity, and for drag and lift, that is at 0.7 times of v takeoff velocity. From here, if you observe, what do we mean by 0.7 times of v takeoff velocity? We have drag at 0.7 times of v takeoff velocity as this, which is half rho v square, and v over here is 0.7 times of v takeoff, 0.7 times of v takeoff, and this whole is in square, half rho v square s cd it is. So half rho v square s cd we know for drag is cd naught plus cdi. Okay, from drag polar equation we know cd is equal to cd naught plus cdi. Similarly, we do the same thing for this lift, which is L equals half rho v square is 0.7 times of v takeoff square, s c l will be there. Okay, so now v takeoff is 1.2 times of v stall, and v stall is the minimum velocity with which an aircraft can fly. Okay, so v stall is given by under root 2 times of w takeoff by rho s cl max, because stall occurs when cl is max, and v takeoff is 1.2 times of v stall. Okay, so we now know these parameters, that is drag at 0.7 v takeoff, average acceleration is also at 0.7 times of v takeoff. And so if now we see or observe this equation of motion, or dumbbell this equation of motion, we have this acceleration as average acceleration, which is at 0.7 times of v takeoff, and we move this to over here with g by w, and g by w takeoff multiplied by this whole term. Okay, this equation of motion, which is now we know it is at 0.7 times of v takeoff. Okay, thrust, drag, lift are function of v square, and we are taking for 0.7 times of v takeoff. And here from equation of motion, okay, v square minus u square equal to 2as, we can substitute over here as takeoff velocity square minus u square equals to 2 times a average at 0.7 times of v takeoff multiplied by ground distance. Okay, this sg. Okay, so here we know that u is 0 because it is starting from 0 velocity, and from here we get sg, this sg equals to v square divided by 2a average at 0.7 v takeoff. So here if we see that drag, which is half rho v square, that is 0.7 v takeoff square, s cd plus cd naught plus cdi. Okay, so here if we talk about the aircraft which is moving on this horizontal plane, or say surface, now this, while moving on the runway, the aircraft will be floating a little bit. Why? As we know, during the flying or say cruising, the aircraft experiences a downward force. Okay, so what downward force it experiences? Let's say the aircraft has these wings. Okay, so the velocity with which the air is coming. Okay, so this aircraft is moving in this direction, and the velocity with which the air is coming, it has some pressure below and upward. So the pressure developed below is higher in the wing and lower above. So the pressure air that is above below tries to move upward. So this creates a vortex. Okay, like this. Okay, so it keep on moving downwards. If you see, its action will be downwards. It comes from above and it moves here above. Similarly, the air comes from below and moves above. So this moves shows the downward force or the downward movement of this air. Okay, so this downward movement is what is creating the induced drag. Okay, so this induced drag that is created by this downward movement of this force creates a downwash along the span of this wing, and this downwash has some strength. Okay, because it is creating some drag or reducing a little amount of lift which is required to lift the aircraft, but it is being dissipated in the downwash by the air. So this downwash is, we are seeing over here, while aircraft is moving on the ground, this downwash gets interfered with the surface of the earth, and while the aircraft is flying high above the earth surface, the aircraft does not have any interference with anything, so the downwash have its original strength which is there. But as it comes closer to the earth, the interference with the earth makes the downwash strength dissipate. Okay, so the dissipation of the downwash signifies that the drag because of this downwash, induced drag, has decreased. So, and that induced drag, when it is decreased, it experiences the aircraft actually, which was having L by D lower before, now it will have L by D ratio increased because the drag has decreased. So which is why it experiences the floating effect, which is also known as the ground effect. It is because of the presence of ground, or say aircraft while flying closer to the ground experiences decrease in induced drag particularly, which creates the aircraft a floating effect. Okay, that makes aircraft fly earlier, we can say. Okay, so now if we say that phi is for to compensate this ground effect, which is less than 1. Okay, so CDI we know is the induced drag. Okay, but CDI has reduced by what amount? We compute that by knowing this phi. So what is phi? In the drag, if we see, half rho v square is given by q infinity, and this drag, as we did over here, is at 0.7 times of v takeoff. Here also it is at 0.7 times of v takeoff. So here velocity will be 0.7 times of v takeoff square. So about the ground effect, we are talking that drag is half rho v square times s cd naught plus phi times CDI, because the amount by which CDI has reduced will be multiplied by the induced drag, because it has reduced by phi amount, and this phi is given by 16 times h by b whole square divided by 1 plus 16 h by b whole square. So h is the height at which the aircraft is flying above the earth's surface. H is not the height, but let's say the aircraft is standing, okay, on the surface or runway. The height of the wing above the earth is h, and the span b is the span of the wing. So h is the height from the surface to the wing span, okay, and b is the span of the wing from one tip to another tip. So now if we substitute these values for 0.7 v takeoff drag, 0.7 v takeoff for lift and thrust, and now these values are being substituted over here for computing this ground distance. So this ground distance is sg equals to v takeoff square. V takeoff is 1.2 times of this whole square, okay, which is above over here, and divide by this average acceleration, okay, this 2 times of average acceleration at 0.7 times of v takeoff, okay. This whole is brought down, okay, and w takeoff is divided by in this whole denominator with all these terms, okay, over here. So and this w takeoff above, which is over here, gets cancelled out, okay. So here if you see sg is equal to 1.44 times w by s at takeoff weight for w takeoff weight divided by g times rho infinity cl max. Now this is whole multiplied with this denominator at 0.7 times of v takeoff, and this is t by w takeoff minus d by w takeoff minus mu times 1 minus l by w takeoff, okay. This is all at 0.7 times of v takeoff. So let's say the thrust that is produced by the aircraft to move forward is very high as compared to the drag produced over this aircraft, okay, and also the frictional force over this aircraft R is also less as compared to this thrust. So from this we can say these two will get down to 0, and we will be left with this. So here we have sg, that is this distance, is equal to 1.44 times w takeoff square divided by g times rho infinity s cl max multiplied by thrust, okay. So with this we will continue with from this rotational distance, transitional distance, and climb in the next lecture. Thank you.